Hello everyone, welcome to this lecture in which we're going to be looking at ANOVA. So by the end of this session and the directed activities, you should have a good idea of when and why you would use ANOVA in relation to research design issues and data assumption checks, and the sorts of research questions it can help you answer. You should have an idea of how ANOVA works, and what it can tell you and what you need to do to probe any findings further. You should have an idea of what to do in kind of common help scenarios, so dealing with messy data, which is often the case with real world data. And you should have an idea of how to report ANOVA and some of the strengths and the limitations of using ANOVA as an approach. The example I'm going to be drawing on today will be my experiences of using a fairly complex design ANOVA in my PhD research. So that was looking at data from a quasi-experimental study where I looked at the impact of victim and perpetrator gender on the acceptance of different types of rape myth. So different stereotypes about victims and perpetrators of sexual violence. If at any point you feel you need to have a break from this, then do. I'm not going to go into a huge amount of detail, but yes, it will be a slightly sensitive topic. The control variables I used as well were observer gender and gender-linked social roles attitudes. So gender-linked social roles attitudes are those that are associated with higher schools, are associated with more traditional beliefs about there are certain roles, social roles, that men and women should do, and they are separate from each other. So I use those as control variables because the literature suggests that they have a big impact on acceptance of different types of myth. So that's the example I'm going to be returning to, mainly in terms of the challenges I had when I was trying to analyse the data, dealing with messy data, making decisions about variables and so on. So what is ANOVA? So ANOVA actually stands for Analysis of Variance. It's usually described as a test of difference. So we're going to be looking at the differences between certain groups or between the same group of individual across multiple conditions or time points. So we usually refer to it as a test of difference. It is a parametric test, which means it makes certain assumptions about the way that your data behaves. And one of those is about the mean. So the mean is the thing that it's actually comparing between the groups or across the conditions. So it assumes that the mean is a good representation of the average response, the typical response in your data set. And that's where the parametric assumptions come in. And we'll look at those in a little bit. So it's an approach that you would use if you have two or more groups or conditions you want to compare. And if you have, you could have one or two or more categorical IVs. You would use it in a combination of different situations. So that should say one or more categorical IVs. But you can only look at it in relation to one DV, one dependent variable at a time. So you might be looking at this thinking, well, if I've got two groups and I want to compare them, I've only got the two groups, one IV with two levels, and I want to compare them on a single DV, then you could just do a t-test. So what's to stop me if I have, say, three or more groups of just doing multiple t-tests? Why couldn't I just compare each group with every other group? And primarily it's an issue to do with our friends type 1 and type 2 error. So type 1 error is where you say that there is something going on and actually there isn't, so it's a false positive. Type 2 error is where you say there's nothing going on when actually there is, which is a false negative. What would happen if you did multiple t-tests instead of one ANOVA is that you would increase the risk of false positive. So it's cumulative, so you have a when we use our p-value of 0.05, that means every 5 times out of 100, if we did the same experiment 100 times, 5 times out of that we would make a false positive, we would make a mistake, a type 1 error. And each time that you do that test, that 0.5 is cumulative. So if you do multiple t-tests, you're just adding up the likelihood of making this type 1 error of a false positive. So what we need is something that's a bit more parsimonious to say, is there something going on overall first before we start to look at the specific differences between the groups? And that's what ANOVA does. So ANOVA is a technique that is based on the general linear model. So you will have encountered this when you've looked at things like factor analysis, when you've looked at things like correlation, regression, and even MANOVA can be considered, according to Tabachnik and Fiddle, a special case of the general linear model. And essentially what it does is it fits lines to things, and it looks at the relationship between different variables and the ability to predict someone's score based on information you have on other variables. And so it kind of follows a similar approach in a way to regression. And in fact, a lot of the issues you could look at with ANOVA, you could convert and look at it using regression, and vice versa. So ANOVA is part of this general linear model. And so what it's actually looking at is whether it allows you to test the null hypothesis when you have more than 2 levels of an IV, and also if you have more than one IV with multiple levels. So the IVs should be categorical, as we said earlier. In fact, what it's doing is it's comparing the null hypothesis that all means are equal, so there's no difference between the means, with your alternative hypothesis that there is a significant difference somewhere between the means. So it's what we call an omnibus test. It will just tell you that if you have 3 groups, if there's a significant result, then there's a difference in somewhere in the 3 means groups. In the 3 groups means. So it won't tell you where that difference is. It'll just tell you that it exists. What you would then do is probe that further. You'll quite often come across certain terminology when people are referring to ANOVA. You might hear them saying a one-way ANOVA, a two-way ANOVA, a three-way, or so on. A one-way ANOVA, or what that is doing, if it's one-way or two-way or three-way, it's telling you how many independent variables you have. So in a one-way ANOVA, you know you have only one IV. A two-way ANOVA, you have 2 IVs, three-way, 3 IVs, and so on. You may also see that some people refer to it in kind of language like a 2x3 ANOVA was performed. What that is doing is telling you a little bit more information about your independent variables. So it's telling you that your first independent variable, which is represented by 2 here, has 2 levels. So a 2x3 ANOVA is where you have a second IV with 3 levels. So your first IV has 2 levels, your second IV has 3 levels. So we know quite a bit more about the design of that ANOVA there. So you might see it written in a variety of ways. In the example that I did in my research, it was actually a 2x2x2x3x4 mixed methods ANOVA. And I'll come on to what the mixed methods bit means in a moment. So what you can tell from that is my first IV had 2 levels, my second IV had 2 levels, my third IV had 2 levels, my fourth IV had 3 levels, and my fifth IV had 4 levels. So it was quite a complex design, and actually, unless you've got a very particular reason for doing this, you should. The recommendations are that you don't go for as complex a design if you can help it. If you can break it down further into a smaller set of independent variables, then you should do. But I needed to look at these things for a specific reason. So you'll notice there that I said mixed methods. So when you have an ANOVA, you can either have a between groups ANOVA, which is also sometimes called unrelated ANOVA or independent ANOVA. And that's where a participant only appears in one level of each of your IVs. For example, my first IV had 2 levels, and that the variable was the observer gender. And so a participant was either identified in this research or self-identified as either male or female. So they appeared only once in one of those levels of the IV. So that would be a between groups factor. What you could have is an ANOVA where if you've only got the one IV, it's a between groups variable. If you've got multiple IVs, if you see it labelled as between groups, it means that each variable is a between groups variable. So you'd only appear in one level. So for example, my second IV was also a between groups variable, and it was about gender-linked social role attitudes, and people were either high in that or they were low in that. And so that's another between groups level. And so if I only had those 2 IVs, each person would either identify as male or female, and they'd either be identified as either high or low in social roles attitudes. So they'd only appear in one cell of the design, which is a subgroup of the design. And I would refer to that then as a 2-way between groups ANOVA. But I've actually got what I call a mixed methods ANOVA. Others refer to it as mixed ANOVA. Some people refer to it as mixed research ANOVA, I think. Mixed models ANOVA. I prefer the term mixed methods ANOVA, but you will see it referred to in different ways in the literature. And that's because one of my variables was a repeated measures variable, and that was actually IV number 5. So what that means is that there were different types of myth that people answered questions about. One of them was called the significance of rape. One was about the credibility of rape claims. Another was about victim deservedness, and the last one was about victim resistance and character. So these were all different types of myth that have been identified in the literature, and this is based on the Rape Attitudinal Questionnaire by Granger, 2008. And so each person completed questions about each of those types of myth. So actually what that means is they appear in each cell of that, each level of that independent variable. We have repeated measurements of their level of agreement across each myth type, which says as the myth type is basically a condition. So each person took part in each part of those conditions. So what that means is I've got a combination of both between groups and repeated measures variables. So it's a mixed methods ANOVA, and that's how I've described it. Okay, so I typically refer to it as a 5-way mixed methods ANOVA rather than going to that much detail, 2 by 2 by 2 by 3 by 4. It's too much. Okay, so example research questions. So we're starting to get an idea of the kind of, perhaps the kinds of designs we might be able to use this with. But what kinds of questions could it help you to answer? Well, the first one, so do victim gender, perpetrator gender, and observer characteristics, a type of myth, influence the degree to which myths are accepted? So that was actually the research question of my study. But there are other examples that I've paraphrased from the literature, which will give you an idea of the versatility of ANOVA. So the complex exercises, which require cognitive demands and various motions, have a positive effect on executive function compared with simple exercise. So there we can see that we've got a sort of between groups approach, perhaps. Are there significant differences in graduate record of examination, verbal and quantitative scores between men and women, PhD completers and non-completers? So what we've got there looks like it might be a mixed method. So you've either got completers or non-completers. You've got examples of verbal and quantitative scores. And there's an example, how does learning from the Iowa gambling task occur between 2 sessions, and what impact does it does a period of intervening sleep between sessions have on learning? Okay, so each of these could be explored using a different kind of ANOVA. And so this comes to kind of these designs, and actually I've got a link here to 3 different articles that use different approaches. So one takes a between groups approach, one is for a repeated measures design, and one has a mixed design, so mixed methods ANOVA. So I put a link here to each of those so that you could read at least the abstract and have a skim over the results section and look at the conclusions that they draw as a result. So you get a sense of the differences between these kinds of research questions and how ANOVA can help you answer them. Actually, ANOVA can be used in a wide variety of research designs themselves. So, for example, cross-sectional, quite often it's used in cross-sectional research, and I've done something similar with Berry, where we've explored data from the crime survey for England and Wales and looked at differences between groups and things like that in their experience of victimisation. It could be used within a quasi-experimental design. That's the example that I've provided for my chapter in my PhD. Or it could be observational designs or so on. So actually it fits very well within a quantitative approach. And actually sometimes what you'll find is people have quantitized qualitative data and then analysed it using ANOVA as well. So it can have quite a wide variety of uses, and it can fit with a wide variety of research designs. So when do we use it? As I said, it's when you have one or more independent variables which are categorical. You can only look at one dependent variable at a time, and that must be continuous. And that's because we're comparing differences between means. So it's got to be something, a variable that you could look at a mean of appropriately. So it has to be a continuous scale level variable, so either interval or ratio level. It has a range of parametric assumptions, as I mentioned. So it assumes that your data is normally distributed around each level of your IV. So not just on its own, but within each level, within each group or subgroup or condition or the differences between conditions, that sort of thing. So data is normally distributed around each level of the independent variable or independent variables. And that's because we're assuming that the mean tells us something about the typical response. So that requires it to have a normal distribution, or roughly normal, really, is what we're aiming for. It assumes that the observations are independent, where you have between groups elements. And also that my score, for example, wouldn't influence your score on something else. That's the kind of the gist of it. So my score shouldn't be influencing your score on some other on your kind of go at the variable, that sort of thing. So it assumes that observations are independent. It assumes if you have a between groups element that the variances, the spread outness in scores for each group is roughly similar. So it's similar. If you've got a within groups element, then it assumes that the variances between the conditions is similar. And so we will be looking at how each of those things can be assessed and what to do if you have problems as well. And it's really important that you have adequate sample size for each cell of the design. So the more complicated your research is, the more subgroups of an analysis, the more cells you have in a design, the more difficult it is to decide what is an adequate sample size. If it's a one-way ANOVA, then the guidance is fairly straightforward. There's a link that to Brycebert's article, 2019 article there, which talks about really robust sample sizes for one-way ANOVA between groups and repeated measures, so that's worth a look at. You can also calculate it in a quite straightforward manner using G-Power, which is a big power calculator. So it can be used to help you decide what sample size you need prior to doing your research and so on, as well as looking at things like sensitivity power analysis. So when you conducted your research, what was the smallest effect you could have identified if you weren't able to recruit as many participants as you really wanted to. So G-Power is quite versatile in that respect. The issue is, though, that the more complicated your designs, the more challenging it is. And you can see Bryce Burt's argument about that. And in particular, if you have more than one repeated measures element, if you have multiple between groups measurements, it can become very complicated very quickly. And that's usually because of things like the interaction effect. What you'll see in a little bit is that there are multiple things that a complex ANOVA will tell you, and that actually what you're really interested in, which of those effects you're interested in, is probably the biggest determination of the sample size. If you have a really complicated design, particularly if you have multiple repeated measures variables, then you'll need to use a different kind of calculator to G-Power. G-Power can only handle one repeated measures ANOVA element at a time. So the only one that I found really that will do the job and that's pretty flexible and fairly straightforward to use is something called BLIMPs. So I've put a link here to that. So the first link is the actual sample size calculator, and then the second link is the manual for BLIMPs. So if you've got a really complicated design, that's probably the only one you can use. Otherwise, you'll need to take an approach similar to Bryce Burt's and look at running simulations based on your specific design, which gets complicated very quickly. One of the things as well, as I've mentioned, is that if you have a one-way ANOVA, the only things that you look at, the only thing you can see is something called the main effect. So it's the effect of whatever your only IV is on the outcome. When you have a two-way ANOVA or more three-way ANOVA, what will be produced is a test for the main effects of each of your independent variables, and then a test for the interaction effect. So whether your two main effects work in isolation, or are they contingent on each other? Does the one moderate the other? And so that's what's really useful about a two-way ANOVA, is exploring that interaction effect, whether one effect is contingent on the other. What you can do is, if you find you have a statistically significant interaction effect, is you'll need to break that down and potentially, and there are a few ways you can do that, and we're going to look at those. Okay, we're starting to get a sense of when we might use, the kinds of questions that we could use ANOVA to help us answer. So we're getting a sense of what's going on, but what does it really mean, analysis of variance? So I like to think of variance as the spread outness of scores in your data set. If you're not familiar with variance, so it's an estimate of the average variability in a data set is technically what it is. If you're not too sure about what variance is, I'd suggest watching this video here. It's really useful to illustrate what variance is in a conceptual way. So it's actually using interpretive dance. It was co-produced by Andy Field, and I would watch this. So if you're not sure about what variance is, pause this video now and watch this video, variance through interpretive dance video first. Okay, so I'm going to assume you've paused the video, watch that. You have a better idea now of what variance is, so we're going to go on. So what analysis of variance does is it partitions variance according to its different sources. So according to its different causes, essentially. And there are different, we anticipate that there are different causes of variance. So there are different things that impact on someone's scores on a measure. The thing that we're really interested in is the treatment effect, which is the whatever our IV is, the thing that we've manipulated or that's naturally occurring differences that we have recorded and that we're looking at whether it has an impact on something else. So we're really interested in the treatment effect. And so that would suggest if you find that there's a lot of variance explained by the treatment effect, it would suggest that there are genuine differences between the groups or conditions, that there is something going on, or IV does have an impact. The other cause of variance is about individual differences. So even if you control all of the setting in which someone takes part in the study, so they take part in the study in the same way, and you control for any other outside variables that could impact on their scores on the dependent variable, it's still likely that there will be individual differences between your participants that will account for some variance. So there will be, it's unlikely that all the people in the same group will be exactly the same. So we have to account for that, these individual differences. And if that's a between groups design, then that's particularly important. What we don't want to have is two groups that just happen to be quite different from each other, and that's why we see an impact on the outcome, and it's got nothing to do with the treatment effect. So we need to identify the impact of individual differences on variance. And there's also things like random error. So it may be things that we, our measurements will never be perfect of whatever our outcome variable is. There'll be some level of error in measurement, some issue with reliability. Even if it's a really good tool, there will be something. It could be things, again, that we can't exactly control for, that could be impacting. Things that we can't really predict, there'll be random error. And each of these things can affect the variance, the spread outness in the scores that we are measuring as our outcome or dependent variable. Okay, so how do we actually calculate variance? And this is fundamental, really, to understanding any techniques that are badged under the general linear model. So if you understand the idea of variance in relation to this, it will also help you with things like correlation and regression and factor analysis and so on. But let's imagine that we have a set of three participants' data. So what we've got here, we've got a variable which is x. X usually denotes your independent variable. Okay, so we've got a score. Each of these rows represents one person's result on x. So the first person scored 1, the second person scored 2, the third person scored 3. And what we first need to do is, with that set of data, we've got to work out the mean for this set of data on x. And that's represented as x bar. So that's the mean for our group here on x. And what we know is if we add 1, 2, and 3 up and we divide it by 3, then we've got a mean of 2 across all our data points. We have a mean of 2. So in this column, we would add in what the x bar is, the mean of our group. So we've got 2, 2, and 2. What we need to do is take each person's score and subtract x bar, the mean of the group. In this case here. So the mean of the data. So in the first one, we'd have 1 minus the mean of the group, which is 2 here. So that would be minus 1. The next one, 2 minus the mean of the group 2 would be 0. 3 minus the mean would be the mean is 2, so that will be 1. And so what we've got here are people's deviations away, how far away from the mean they are. And so what we've got to do now is, though, to be able to calculate things in a really meaningful way, so we've got to take the distance, we need a measure of the distance away from the mean without worrying about the direction. And so the best way of removing the direction of a number in terms of whether it's a minus number or a positive number is to square it. And so that's what we've done here. So if we square 1, it's 1. If we square 0, it's 0. If we square minus 1, it's 1. And so all of those numbers are now positive. They show us how far away. So these are the squares. How far away our data point is here from the mean of the data points here. So the bigger the difference between these two, the further away from the mean they are. And so what we've got here are squared values for each individual. What's really useful is if we sum these, and that's what this whole row is here on the top of this equation. So that's sigma, and it means sum, the sum of. And so what we have here would be the sum of squares, which would be 2. And then what we need to do is divide that by the number of observations, so the number of participants we have, and that would give us the measure of variance in this data. And so that underpins lots of approaches in terms of ANOVA regression, and you'll see people referring to the sum of squares, and that's what this is. And what SPSS will do, what you would do by hand if you needed to, would be to look at these sum of squares and to help you understand variance and how it's portioned up differently based on whether you're associating it with the grand mean, which would be all of the data, or particular group means. If you've got a between subjects design, then the difference between males and females, and so on. And so how you calculate variance does depend ultimately on what mean you're interested in. And if you look at things like Eugene O'Loughlin's YouTube page, he will talk you through calculating ANOVA by hand or correlation, all those sorts of things. And it's a way of portioning up variance. But you'd either use the grand mean, which is the mean of all of the data, or the group mean, the group of the independent variable that they belong to, or the condition that they're in. And you use that to explore whether that is a better fit of the variance in your data than just using the big grand mean. And we'll see how that works in practice with between groups and repeated measures elements as we go along. But that's at the heart of what variance is and how it's calculated. So we use that portioning up of variance to produce a test of statistical significance with ANOVA. As I said, it's called an omnibus test. And what we've got is we'd actually calculate something called the F ratio with our data. And that's calculated slightly differently in respect with between groups ANOVA as opposed to a repeated measures ANOVA. And we'll look at that in a moment. But what we would do is we would use the portioning up of variance to calculate the F value, the F ratio. Then if we're doing this by hand, we would compare it to a table of critical values of F. And if our F ratio was larger than the critical value, which is based on the number of variables we have, the number of conditions potentially, the number of participants, that sort of thing. If our F ratio is larger than the critical value, then our statistical test would be significant at that level. So luckily, SPSS will calculate all of this for you. You don't have to go rooting through tables of critical values for F, which is the distribution of F, how it should behave based on different sizes of study and different numbers of variables and so on. So in terms of how ANOVA uses variance to do this, as I said, we need to look at things differently if it's a between groups analysis or repeated measures. So we'll start with between groups analysis because I think this is actually, it's more intuitive. So what you're doing is you're testing the null hypothesis that all conditions have the same population mean. Then what we're looking at is saying that the total variance in scores are based on the variance between the groups, i.e. between the group means, and the variance within the groups, the variance between the scores within the group, which could be due to individual differences or random error, that sort of thing. And what we want to do is compare the difference between the treatment and the error variance. And what that means is we calculate a ratio. So we look at the difference in variance between the groups. Is that larger than the difference of the within the groups? If it is, if the variance is smaller within the groups than it is between the groups, then it suggests that partitioning the variance in this way makes sense, so that it helps us to explain people's scores on the outcome. So let's have a look at that in practice. So let's imagine we've got 3 different groups. It's a between groups analysis. They've all taken part in something and they've all recorded a score on that outcome variable. So perhaps in this case, we'll just say it's some sort of rating scale from 1 to 10. So if we're looking at group 1, group 2 and group 3, what could you tell me just from eyeballing that data in terms of within group variance and between group variance? So just pause the video and think about it for a moment. What could you tell just from looking at those numbers? Okay, so what we can see, everyone in group 1 scores 9, everyone in group 2 scores 2, everyone in group 3 scores 5. So there is absolutely no within group variance. Everyone within a group scores exactly the same. There's no variability in those scores. But if we compare them between the scores, between the groups, there is, I'd say, fairly substantial between group variance. So the average score for group 1 would be 9, the average score for group 2 would be 2, and the average score for group 3 would be 5. So what we can see is that actually being in a group does tell you something about the score, in all likelihood. Whereas if you ignore the groups, the error within the group, the variance within the group is very minimal. So it does suggest that actually splitting people up into groups does tell us something meaningful about their score. And that's what this does. So the F ratio for a between groups analysis looks at the ratio of between group variance, which we saw a lot of in the last example, over within group variance, which we saw absolutely none of. And if between group variance is larger than within group variance, your F ratio will be bigger. The bigger the F ratio is, the more likely it is to be statistically significant. That is, there is a genuine difference somewhere between your groups. So that's what the ANOVA will tell you. And so technically what it's called is it's the mean squares of between groups with the mean squares of within groups. And that's what you're comparing. So we saw how we calculated the sum of squares. What you take is the mean of those, and it would be the mean squares between groups and the mean squares within groups. And that's what F is. That's what the statistical test is. So there's a really useful link at the bottom of this page that you can access freely via Laird Statistics, and it takes you through exactly how this is calculated and kind of the reasoning behind it. So I would, if you're at all unsure about what's going on, I would pause this video now and have a look at that, and I think that will help. So if we have a look, also there's the example paper. Okay, so that was for the between groups analysis. It's very similar if you're looking at a repeated measures analysis in terms of how the F ratio works, but there is a subtle difference. Obviously, if it's purely repeated measures, there is no between groups element for you to compare between. So what we have to do is consider rather than the null hypothesis being that the the population means are all the same across groups, what we're saying is that all the conditions will have the same population mean. So it's thinking about those levels of your IV as a conditional time point instead. So what we're saying is instead of the total variance being the variance between groups, is that the variance it's between conditions or time points plus the variance within the conditions, which comprises the kind of the variability between individuals and the error variability as well. So ANOVA partitions this up into, again, total variance, this total variance into the treatment variance and the error variance. So it's very similar in some respects to the between groups, but we'll look at how it's calculated. There's a slight difference in a moment. So again, let's have a look at this. Imagine this time we've got the same group of people with a rating, again, from 1 to 10. But we start at time point 1. Perhaps it's how anxious are you about statistics at the beginning of this lecture, and you measure each person on their score of anxiety at time point 1, and you can see time point 1, time point 2, and again the same measure for each person at time point 3. So looking at that, what could you tell me about the within condition variance and the between condition variance? So just pause this for a moment and have a go at that. Yes, so it's similar to the first example we showed you. So there's no within condition variance. So again, at time point 1, everyone's really anxious. At time point 2, they're a lot less anxious, and at time point 3, there is the anxiety is as low as it possibly could be. So that's good. There is between condition variance, as I said. So you see this change in a person's score reliably across time point 1, time point 2, time point 3, but within the conditions there's absolutely no variance. They're all scoring the same thing. And so your F ratio will look something like this. So it's the conditions variance over within group variance, which is the individual variability. And so what you'll actually see is it's sometimes referred to in this way. So MS time, MS error, so mean square time over mean square error, or MS conditions over MS error. And so there's a really good walk through again of how this is calculated and why by layered statistics on the repeated measures. So I would recommend having a look at that. And I've also put the link to the repeated measures analysis paper there, so you can get a sense of the differences between reporting and interpreting between groups analysis and within groups or repeated measures analysis. Okay. So, as I said, ANOVA uses variance in slightly different ways in terms of between groups and within groups. So what happens in mixed methods? Well, essentially it does a bit of both. What mixed methods automatically tells you though is that you have examples, you have both a between groups element and a within groups element, so you have to have at least 2 variables for mixed methods. So what that means is you have a main effect, so all the groups have equal means. You'd have main effect for the groups, main effect for the conditions, but you'd also have an interaction effect. And so this is what ANOVA starts to do is kind of, and this is a good illustration, it starts to break it down into these different portions of variance. So the amount of variance explained by the main effects and the amount of variance explained by the interaction effect. So whether the groups versus the treatment conditions or considered together help you understand patterns of variability in your outcome variable. So if we have an example, and I think to show this, I need to put it into a table. So what we can see here is in the one column, we've got information on whether someone is in the control group, for example, or whether someone is in the treatment group. And what we've got here is the within groups element, which is everyone took part in the assessment before and after an intervention. So just looking at that, what can you tell me? Looking at the within condition variance, what can you tell me in terms of the between condition variance? What might you be able to tell me in terms of between the two, an interaction? Okay, so what we're looking at is trying to portion up this variance. So the main effective group would be if we took an average of across before and after, and we looked at that ignoring time points, so an average of these scores, and we looked at the difference between groups 1 and 2. And so we probably would find some form of difference between these two based on that. Within condition variance would be comparing before and after, ignoring the group that someone belongs to. Again, so taking an average of this and an average of that, and looking at whether there's a difference between the two. So that would be the main effect of the within condition variable. Again, we probably find something going on. But actually what we'd probably be particularly interested in is this idea of the mix of the two. So when we take into account someone's group, when we take into account before and after, what we can see are these different subsets of scores. So they do seem to be these pockets of different scores which would relate to different means. And actually, it would suggest that probably, if we did the analysis based on this, there would probably be an interaction. And actually, when you have an interaction effect that involves your main effect, you should put a lot more weight on interpreting that than the main effects involved, because actually they're misleading, that the group variable is contingent on knowing if it's before or after or so on. And so actually how it's calculated, that's a bit fuzzy, sorry. So how it's calculated is that you would have an F ratio for the first factor, factor A, which would be group, for example. You'd have another factor, an F ratio for your second IV, factor B, and then you would calculate another F ratio for the effect, so the interaction between factor A and factor B, and that's what each of these formulas represents. And there's quite a good talk through in terms of how that works on this blog post here. So I'd have a look, pause the video now and have a look at that if you're unsure about what's going on. But what would happen is you'd have a test for the main effect of group, a test for the main effect of time point before and after, and a test for the interaction between the two. And that would give you an idea of really what is going on. Okay. So our F ratio is the thing that we use to calculate a p-value. So we know that the larger the F ratio, the more likely something is to be statistically significant. But actually, it's not the only part of the story that's important. As I said already, if you've got more than two groups, then you'd have to do follow-up analyses, because all the F ratio would tell you is that there is a difference somewhere between your three groups, for example, but not exactly where. It could be that each mean for each group is different from the other, or it could be that only two of the means are different from each other. So you'd have to explore it further. But even if you explored that further and found a significant effect, it's not the only thing that counts. We also need to get an idea of whether that significant result is meaningful or not. So you could have a statistically significant difference, but actually the differences between the groups is so small that in practice it wouldn't be beneficial, it wouldn't be helpful. So to help us to decide that, what we need to do is to look at measures of effect. So effect size refers to the magnitude of the difference between the groups, or the strength of the relationship between the variables, that sort of thing. So actually, a p-value on its own just tells you, as this example illustrates, that depending on your sample size, all it does is it tells you that there is um, a significant difference between the groups somewhere. The larger your sample size, the smaller the difference you can detect. The smaller your sample size, the bigger the effect. So it the bigger the effect has to be able to detect it. So it really does just tell you whether it's a difference is likely to have arisen if the null hypothesis was true or not how important the size of the difference is. That's what you need the effect size to do. There are lots of different types of effect size. The one that SPSS calculates in relation to ANOVA is actually partial eta squared or eta squared, which is the last example in the table. The one that is most commonly used is Cohen's d, and there are actually calculators out there that will allow you to convert one thing to another. So it gives us an idea that using whichever effect size you use, and some are better than others, but it gives you an idea of, well, how big, is the effect I've identified? Is it useful? Is it important? How impactful is the independent variable or treatment, for example. So what we've got here are some rough guidelines that give us an idea of what a small-sized effect is, what a medium-sized effect is, and a large-sized effect. And there are different arguments about what's useful to know. So a large-sized effect is obviously the biggest thing you could detect. Usually it's where you could see the differences between the means of the groups, and they look obviously very different from each other. But there's an issue about whether that's potentially is useful in psychology, because we might be interested in more subtle effects that aren't easily identified by the naked eye then, but that could still be useful to us and help us understand the differences between groups or the effectiveness of an intervention, that sort of thing. So actually in practice, we're probably really interested in the medium-sized effects, which is where we really should use statistical testing to be able to identify them. That is useful for helping us to try and predict the sample size that we need. So usually if you're not sure what sized effect there is in the population, then the guidance is to base your calculations on trying to identify. So how many participants do I need to identify a medium-sized effect if one really exists? And so we get an idea for partial eta squared that a small-sized effect is 0.01, a medium-sized effect is 0.06, and a large-sized effect is 0.14. In theory, partial eta squared can just get bigger and bigger. Some of them are constrained, to fall up to 1, and others aren't. So an example then. So if we think about a finding that I had from my PhD, so I identified a 4-way interaction effect, that it was statistically significant. So I identified that was between myth type, that was the repeated measures variable, gender-linked social roles, victim gender and perpetrator gender, which were between groups elements. So there was something going on between those 4 variables that was meaningful about the scores on acceptance of these myths. So there was something going on between these 4 different variables that would help me understand why people scored differently on the different on accepting of rape myths. What I also identified, so that's what this part of the output is telling you. So the p-value was 0.035, but I unfortunately found that was quite a small-sized effect. So only just crept over the small sized effect. So 0.013, that was partial eta squared. So I'd have to decide if that was practically useful or not. Okay, so what do we do then? If we find that there is a difference somewhere, and we've got more than 2 levels, We just know that. There's a difference somewhere, we don't know where. We've got to do some more testing. If you find an interaction effect, as I said, that involves some of the main effects, then you should interpret that interaction effect, give that primacy rather than the main effects, because you know that they are misleading. They can't be considered on their own, they're contingent on the other variables. So to do this, you'll have to follow each of these things up in some way, and there are different approaches. One of them is to just present descriptive statistics and profile plots. And it depends. That's the approach I actually took in my PhD because I had so many variables that testing explicitly the interaction effects would have massively inflated the risk of a type 1 error. So actually what I did was to explore, and I was more interested in the patterns rather than being able to make really draw concrete conclusions purely on that study, because this was part of a wider program of research. So I wanted to use this to help me to design additional qualitative studies and then to draw all of those things together to generate meta inferences. So this wasn't the end point either. So I made the decision to look at generating descriptive statistics and profile plots to explore these complex interactions rather than testing. But there are ways of explicitly testing differences between, if you have a main effect, differences between the groups or conditions, and also for testing interaction effects, for probing them. The first approach is called planned comparisons of those. The second is post-hoc testing, and we'll come to both of those. And I'll explain what simple effects analysis is. So, profile plots. One of the first things you have to decide is, are you going to generate profile plots instead of other approaches or as well as? As I said, I did instead of, but for smaller numbers of interactions, you might want to just do this to illustrate your post hoc testing, for example. Another decision you'll have to make is about line graphs or bar charts. And actually, Cohen from 2014, so Barry Cohen, provides some good guidelines about interpreting complex interactions. So that's when you've got, say, a three-way interaction, and actually advocating the use of line graphs to help you understand how these things interact at different levels. So I really recommend, if you're thinking about doing a more complex ANOVA, having a look at that chapter that he's made available using that link. And also, line graphs in particular are useful for identifying whether something is called an ordinal or a disordinal interaction. So a disordinal interaction is where they will cross over each other, for example, and that's a really particularly powerful type of interaction. Ordinal is where they may separate out, so the lines kind of move away from each other on the graph, but they don't potentially cross, for example. And so actually line graphs, more than bar charts, can be useful for helping you identify that. So quite often, if I'm asking SPSS to produce a profile plot, I will ask it to produce a line graph first, because I think they're slightly easier to interpret. Planned contrasts are where they're particularly useful when you have a set of very specific follow-up hypotheses, so that in the event you find a statistically significant main effect of something, you know exactly where you think the differences between the groups should be and what direction they should lie in, for example. And in that case, a planned contrast could work better. If you've got a really complicated design, then you might have to create your own. But there are some off-the-shelf, as Andy Field calls them, planned contrasts. Polynomial looks at things like trends, and I'll explain that a little bit more in a moment. Simple is where you compare each of the conditions or groups to a pre-identified reference group. And Helmut takes a slightly different approach, so orthogonal comparisons, so unrelated comparisons, for example. So if you want to learn more about this, I'd recommend having a look at Andy Field's chapter about different contrasts. It's very thorough. Polynomial trends are where you look at things like linear trends across the levels, and what type of trend you look at will depend on how many levels of a variable you have. So if you have 3 levels of a variable that you want to compare, then you could potentially look at a quadratic trend or a linear trend. If you have more than that, then there are other more complicated trends you can look at. But if you've only got 2 groups or 3, then probably linear would be potentially the best approach. But it can be more challenging when you're trying to generate what Field calls robust estimates. So if you violate lots of assumptions and you can't correct for them, it can be more challenging to explore applying contrasts in that context. But then that's the same as well in a lot of respects for more complicated ANOVAs and post hoc tests, as we'll see. But again, have a look at Field if you're interested in understanding more about this and robust estimates for ANOVA. The idea, one of the benefits of using a planned contrast is that it should control for the family-wise error rate, because what it's doing is comparing a subset of levels of your IV with another. It isn't comparing every single possible comparison, which would be pairwise comparisons. So the idea is that by only selecting out a few pre-identified comparisons that you want to make, that you've planned in advance of doing the analysis, that should help to control for the type 1 error. There are differences in opinions on that, but again, have a look at Field for more detail. The limits of planned contrast, as I said, are that only a contrast, you can contrast one portion of variance with another at a time, and then once that initial portion of variance has been used as such, then it can't be used in other comparisons, which can be a challenge. It is really only beneficial to do these when you have specific hypotheses and you know the order in which your levels are coded, that's meaningful, that basically it goes from the smallest anticipated difference to the largest, for example. So if you don't really know what you're going to find, then planned contrasts aren't probably the best use. And as I said, if you have quite a complicated design, you're probably going to have to create your own contrasts rather than using the kind of off-the-shelf options. So the alternative is to do post hoc tests. And if you haven't got a really fixed idea about exactly how your conditions or groups should differ from each other, then this is probably the right option to take. They're more intuitive and they're slightly easier to interpret. What it often means is that you're going to end up doing pairwise comparisons, and that's where you can compare group or condition 1 with group condition 2, group 1 with group 3, and group 2 with group 3. So every possible combination of conditions is compared against each other. There is a difference in how you do this in terms of repeated measures and between groups designs, and I'll come on to that in a moment. There are also, for more straightforward ANOVAs, so one-way ANOVAs, you can produce robust estimates. So if you violate things like the assumption normality, then it is possible to choose types of post hoc tests that can handle that better. But as soon as you start to get more complicated designs, it becomes more difficult. The issue with pairwise comparisons is that you are running the risk of a type 1 error, of increasing that, because you're doing multiple tests. So the more tests you do, the more likely it is that you're going to identify a significant difference, even if it doesn't really exist. So we might have to find other ways of controlling for that if we're going to do pairwise comparisons. And so there are different approaches to that. So the one approach that you can use is called the LSD approach, interestingly, and it's where you have absolutely no correction. So it's the most powerful approach to doing post hoc comparisons, pairwise comparisons, but actually you've got a much higher risk of committing a type 1 error as a result. The flip side of that is to apply the Bonferroni correction, and that's where you take your initial p-value of 0.05 and you divide it by the number of comparisons you're going to do. So your p-value would drop, for example, with 3 comparisons, your p-value would drop to 0.017. So only a significant result of 0.017 or below would be statistically significant rather than 0.05. So the benefits of that is it's unlikely you're going to make a type 1 error as a result, because you've really stringently controlled for that. The issue is it's overly conservative. It massively reduces the power of your analysis, and it makes it very hard to find anything, even if it's genuinely going on. If you're doing a between groups analysis, then the alternative you can use is something called the Tukey test, which I like to think of as the turkey test. But the Tukey test, it fits somewhere in between those two approaches. If you're interested in exploring these more, again, have a look at Andy Field's discussion of post hoc tests. The issue is that the Tukey test is only available for between subjects factors. So you have to bear that in mind. As soon as you have repeated measures, you're going to have to do something different. You can still do pairwise comparisons, but the Tukey isn't necessarily available. So the limits. A pair of post hoc comparisons, post hoc tests. It'll only produce those tests for main effects. It will not do it for an interaction effect. Whereas a planned comparison, it will do it for an interaction effect as well. Although it can be very hard to interpret those. So if you one of the main issues with the post hoc test is if you need it to do it for an interaction effect, then you've got to perform simple main effects instead, and you'll have to do that manually yourself. They're not too laborious. It does depend on your design, how many independent variables you have, and so on, and how many of those are involved in the interaction. But what a simple effect is, a simple main effect, is where you compare 2 or 3 levels, however many levels your first IV has, at each level of your second IV, for example. If you have more than 2 levels of one IV, then you'll also have to do pairwise comparisons on top of that, but that's fairly straightforward. As you can see, the issues with that is, again, you're running many types of analysis, and that can be a major problem for the type 1 error, so the family-wise error rate. So you might think, okay, well, we need to correct for this then. So if you're running multiple analyses, multiple comparisons, then one approach is to apply the Bonferroni correction. But as we've already said, that is extremely conservative. So there are other approaches you can take to try and get the balance between type 1 and type 2 error better in check. So the Bonferroni is a sequential correction. So it takes account of it uses the Bonferroni correction, but it takes into account the number of comparisons you are running. So it kind of manages the type 1 error rate, long run error rate, but it's far less conservative. So the idea is it's got a better balance. And if you want to explore how that's actually done, what's involved, then there's a really good link here to a blog about kind of how that works. So the Bonferroni correction, and that is something I have used actually in my own PhD and other research as well. Another alternative approach, which isn't used very much in the behavioural or social sciences, but is used very much in things like ecological studies, is something called the false detection or false discovery rate. Again, there's a link to the false discovery rate and how it's applied. And that approach is used in things as well like epidemiology, where you've got very large numbers of analyses being run within a single paper, and you want to, again, control for the risk of type 1 error, but not with the impact of massively increasing the risk of type 2 error. And so that's a different approach you can take. And again, that link to the statistics how-to will take you through what that is, so in a bit more detail. But there are alternatives to it. If you have got a lot of analyses you're going to need to do, a lot of follow-up analyses, I would recommend the Holm-Bonferroni correction rather than the Bonferroni correction. So thinking about then my example, as I said, I had a large number of independent variables, and actually I identified quite a higher order interaction effect between 4 of the variables, 4 of my 5 IVs. So trying to interpret that is very difficult. Actually what I did was I explored the descriptor statistics for each of the cells, the subgroups in my data, and I created profile plots following the advice of Cohen, 2014. So based on the adjusted means, and so this is actually the plots that I developed to explore that 4-way interaction between myth type, which was actually you can see the different lines represent the different myths, and I'll talk through that in a moment. Gender-linked social roles, and that's actually how the 2 different plots were provided, were developed, and the social roles groups, so that they were kind of the low and the high groups, and then you've got the perpetrator gender. So I had 3 conditions. You either were being asked about a female perpetrator, male perpetrator, or the perpetrator gender wasn't specified, and female and male victim gender, so split out by victim gender. So as is in that, I kind of argue, as this is a complex interaction effect, descriptive statistics and profile plots, breaking down the interaction first by low and high gender-linked social roles groups. So on the left-hand side are the graphs for the low gender-linked social roles group, and the 2 graphs on the right-hand side are the high in gender-linked social roles group, and then layering the lines by victim and perpetrator, layering the graphs by victim and perpetrator gender, and then the different lines in the chart represent the different kinds of myth. So the blue line represents the significance of rape myths. The green line is victim deservedness myths. The red line is credibility of rape myths, and the orange line is the victim resistance and character myths. And so I explored what these kind of suggest. And for the actually the higher the score, the more rejecting people were of the myths. So you can see in the overall in the lower social roles, gender-linked social roles group, that there is greater rejection overall of the myths compared to the high in gender-linked social roles group of participants. You can also see that when you're looking at, you can see different patterns of effect in relation to if you're being asked to consider a female to victim as opposed to a male victim. And actually what this might suggest is that there's something about male victims that mean that people respond in similar ways to victim deservedness and significance of rape myths, and similar to victim resistance and credibility myths. Whereas for female victims, the credibility myths are the thing that people reject least. They respond in similar ways to victim deservedness and victim resistance and character myths, but they're fairly rejecting of significance of rape myths. So we're actually seeing that there's, across all of these groups, across all these conditions, that there's a complex pattern. People are responding to some of these myths in similar ways, depending on whether you're thinking about male or female victims, and actually whether or not you're drawing attention to the perpetrator gender and what perpetrator gender you're specifying. And people were particularly kind of in the high gender linked social roles group, particularly well, less rejecting of credibility myths in relation to female victims of female perpetrators. So there's something going on there that's important, really important in comparison to some of the other groups and the other patterns as well. And so this is really where I use this research to help plan and explore a qualitative study to try and understand these sorts of profiles, profile plot findings, what was going on. So I didn't test them explicitly. Okay, but you can see how complicated it can become when you have multiple independent variables. And Bryce Burt's recommendation is that if you need to have a good reason for including these variables if you're going to do that with ANOVA, for example, because particularly repeated measures elements, because it can become very confusing very quickly, and it's actually quite hard to interpret the findings of interactions once you start to have multiple independent variables and higher order, what we call higher order interaction effects, so where there are multiple variables in the interaction effect. One other thing to say then is, because I identified this interaction between myth type, gender-linked social roles, victim gender and perpetrator gender, I actually did find a main effect of myth type, a main effect of gender-linked social roles, and but not main effects of victim and perpetrator gender. But what it meant is then I can't interpret the main effects of myth type and gender-linked social roles, because they are contingent on other factors. They're contingent on whether someone is described as a male or female victim, and the perpetrator gender that is described as well. So what it meant is that when I was writing up my results, I had to go into much more detail and place more emphasis on these interaction effects than the main effects themselves. Okay, so what I'd like you to do now is to actually have a go at the walkthrough that's on Blackboard. So it's it takes you through a one-way, you can either do the one-way between groups or the one-way repeated measures example following the link. It's a slightly different walkthrough to some of the others in that it's an online interactive walkthrough. You could do both if you wanted to, but obviously that will take longer. But have a go at doing that for the one-way between groups or one-way repeated measures, and then come back to this video and we'll talk through some of the common help scenarios. So pause this video now, have a go at that, and then come back to this video. Okay, so I'm going to assume that you've had a go at the walkthrough, so you've got a sense of, how it is performed, what it can tell you, and some of the issues about checking your assumptions and dealing with those. Okay, so we're going to look at that and think again about simple ANOVA, but also more complex designs of ANOVA and the impact of that. So I think there are a few different help scenarios, and I encountered quite a few of these when I was doing my own research. But the first one, for example, or the first two are about sample size issues, and they can have a knock-on effect on the other things as well. But sample size issues, if it's a one-way ANOVA, it's fairly simple to calculate, but as soon as you have more than one IV, it becomes quite challenging quite quickly. The next few are about kind of looking at the assumptions of the data, and perhaps prior to doing some of the actual analysis. So they're things that you need to consider for both any type of ANOVA design, but how you do that is slightly different. The Mauchly's test is only if you have a repeated measures variable and it's got more than 2 levels. The Levine's test of homogeneity of error variances is only when you have a between subjects factor. And then I'll talk through again, well, I've got this significant interaction effect, what do I do? Okay, so looking at the first bit, it's all about your research design, and before doing your data collection, thinking about your sample size. So some of the guidance in the Bryce Burt article will take you through some of the research designs. And actually, if you look at his approach, it suggests that using G-power, for example, is slightly underpowered, so it underestimates the sample size you need. And he took the simulation-based approach. And he provides some guidelines. So if you want to be really robust, those are the kinds of numbers that you need to be thinking about. Now, obviously, they're quite hefty, the sample sizes that he recommends. You can use things like G-power to help you estimate. Tabachnik and Fiddle kind of argue that if you have at least 20 degrees of freedom for your your in each cell, so your 20 observations in each cell, then your ANOVA should be fairly robust to moderate violations of things like normality, but that's a slightly separate issue from power. So it may be fairly robust, but it doesn't necessarily mean you're going to have enough power. When you are looking at trying to estimate the number of participants you need for a more complicated ANOVA, then you should think about the effect that you're really interested in, because you need less data to test for a main effect and more data to test for an interaction effect. So if that interaction effect is the thing that you're really interested in, you need to use that to help you guide your sample size calculations. If one of the things you really should be thinking about as well is make sure you collect, or you try to collect, the same amount of data for each group if it's between groups analysis, because that will make interpreting your effects far more easy to do, and it will also help you if you violate some of the assumptions. It's not such a big problem if your groups are roughly equally distributed, so that you've got roughly the same numbers of people in each. If you have very different numbers of people in each of your groups, you violate assumptions in the data, it's a lot harder to correct for them. So try and make sure that you recruit groups that are equal. If they are unequal and you're doing repeated measures, then you can potentially interpret some of your effects using a multivariate test, which can correct for that, using P-Lies trace, for example. But if not, you're going to have to pay a lot more attention to the assumptions, and if you violate them, and if you violate them in identifying whether it's a problem or not. Okay, so thinking about your data doesn't look normally distributed. Now, one of the first things you've got to think about is when you're doing your data assumption checks, how are you going to check this? So if you've only got a one-way ANOVA between groups or repeated measures, then it's fairly straightforward to do this using raw data. But as soon as you have more than one independent variable, you should be checking these assumptions using the residuals from the analysis. And in some of your more complex ANOVA walkthroughs, you'll see that, talking through how that's done. There's also some links in suggested reading to that, and problems with data assumption checking and mistakes that people commonly make. So the first thing is to decide exactly how you need to check the data and check for normal distribution. If you've got outliers, you've got to decide how to deal with them. One approach is to delete the case from the analysis. Another might be something called Windsorizing, which is where you change the extreme case value for the largest non-extreme case value, although obviously there are issues with that. You've just got to be clear about which approach you take and why. They'll all have problems, they'll all have benefits, and so pick the one that you think suits your situation best and evidence it. So put the give a link to the reference, the reference you've used that's helped guided you with that decision making. If you haven't got any outliers but your data is quite skewed, if you've got a fair amount of data, so you, as I said, and you've got equal numbers of people in each group and in each condition, then your ANOVA will be fairly robust to moderate violations. If you've got really extremely skewed data, for example, then you'll have to think about doing something. One approach is that if you're doing a one-way ANOVA is to ask for the robust estimates to be produced. Another approach is to look at transforming your data beforehand. It may be that you can transform the data and that will correct the issue. And again, look at Andy Field's discussion of data transformations to help you choose which one to apply in which situations. it may be that if you're doing a one-way repeated measures or one-way between groups ANOVA, then you can just do the non-parametric alternative and bypass those issues. If you're doing something more complex, there isn't an alternative, a non-parametric alternative that is equivalent. So, for example, if you're doing a two-way repeated measures ANOVA, there is no direct comparison that's non-parametric. You'd have to break it down into all of the different effects you want to test and test them separately. So instead of looking at an interaction effect between your two variables, you'd have to look at simple effects and look at those within a non-parametric ANOVA, for example. So, but there are things you can do. It's just that it becomes more complicated. Okay, so the other issues around Mauchly's test of sphericity and Levine's test of homogeneity of error variances. So it's a good guide if you want to understand sphericity more. Again, look at Laird's statistics. The Mauchly's test of sphericity, if nothing comes up in it, if just the box is produced and there's a dot in it, which does happen, don't worry. It's because your within subject's variable only has two levels. And the assumption of sphericity only makes sense when you have more than two levels. And it's the amount of variance between the different levels of your IV. So if you've only got one difference, so you've got the difference between condition 1 and condition 2, then you don't have to worry about it having the same amount of variance as anything else, because there isn't another comparison to make. If you've got more than 3 levels, then the Mauchly's test will return something. If you violated the assumption, is not to worry. You've got a couple of options and you can have a look at those in your walkthroughs. But you can just use, and I would recommend using, for example, the Greenhouse-Geiser corrected test statistics. They're corrected so that the analysis is slightly more stringent, so that you don't erroneously say there's something going on, that there's an effect of your variable, there's a main effect or an interaction effect. That is purely due to this violation of the assumption. So I would use the Greenhouse-Geiser test statistics. If you violated the Levine's test of homogeneity of variances, it's more problematic. You might need, one of the most straightforward approaches is to lower the p-value at which you would accept statistical significance for the variable that has violated the assumption of the Levine's test. So I would normally drop that from 0.05 to 0.01 and interpret the statistical significance for that variable at that new threshold. It's not ideal, but it's perhaps the best way of correcting for it. I think Julie Pallant mentions it in some detail, in a little bit of detail in her book, the SPSS Survival Manual. But it can cause an issue, and then you should be wary of any effect, an interaction effect that controls, that has that variable included. It could produce a spurious interaction effect. So you have to really scrutinise your data using things like your profile plots really thoroughly to think about whether there is something going on or not. But there are things you can do. As I've said previously about the significant interaction effect, if you've got a significant interaction effect, then you can't place too much weight on interpreting the main effect that interaction effect involves. And also you'll need to probe it in some way, and you'll have to tell the reader what you're doing and why. So if you're going to probe it with interaction plots, or if you're going to test for simple main effects and things like that. So you need to say what you're doing and why. But again, place more weight on the interpretation of those interaction effects than their main effects, because those main effects are contingent on other things, so they are misleading. Okay, so my example, thinking back to my chapter, what did I do? So one of the first things that I had to decide was about checking for normality. I had so many subgroups of analysis that it simply would not be feasible to look at the raw data and how it was distributed for every single subgroup and variation of subgroup. So what I did was, and I put a link to the paper that I used to help me make these decisions, was I used the residuals and I explored the residuals for the to see if they were normally distributed. And there, as I said, there's a link in the suggested reading to a paper that's really useful in describing this and the mistakes that are often made. So I checked the many of the assumptions that I needed to for ANOVA by using the residuals. I also probed the interactions, as I've said, with descriptive statistics, and I followed Cohen's 2014 guidance on using adjusted cell means and standard errors and line graphs to do that. But I had to make the argument as to why I wasn't explicitly testing them. And in terms of the interactions and the main effects, I had to be careful. Some main effects were left untouched because there weren't necessarily interaction involving them. But for example, observer gender. But if they were involved in an interaction effect, a higher order interaction effect, then I was very careful not to place too much emphasis on interpreting the main effects because I knew they were contingent on other variables. And so that's something that, as I was doing that with my own data, I understood that a lot more. So in terms of writing up the good practice, be clear about what your hypothesis is. You may be testing multiple hypotheses using different parts of the ANOVA, or ANOVA might be only part of the analysis you're doing. Be clear about that and be clear about which analysis is testing what. When you're doing things like calculating sample size, base it on a two-tailed significance test. And actually, although technically you could try and have a one-tailed significance test, it doesn't really make sense with ANOVA because you could have a difference in multiple directions if you've got more than two groups or conditions you're comparing. So by default, we should be doing two-tailed significance testing, but that has important implications when you're trying to calculate things like sample size. You need to be clear about the family-wise error rate, whether you think it is a problem or not, and how you've controlled for it. So don't just ignore the issue, you've got to be clear about it to the reader. And use profile plots to illustrate particularly interactions and effects, because they can be quite useful, but also think carefully about, you don't want to just repeat something that's already in a table. So it should add something new to your interpretation, not just repeat something in a different format. That's APA guidelines. Whenever you make a claim about something in the data, whenever you make a decision, for example, about checking normality, about the family-wise error rate control, you need to evidence it. So you can evidence it by providing statistical evidence from your outputs, theoretical evidence, so in your interpretation based on the theory, empirical evidence, other people's approaches and kind of issues that they've overcome and how, but also the guidelines that you have used that have helped you've based your decision making on. So be clear about that, because there are differences in opinion in the literature. APA recommends that purely that you are clear in your writing, you're concise, and that you're consistent in your approach. So it depends on how complex your analysis is as to whether you might need to use text or tables. In terms of ANOVA, you could use either, but obviously the more independent variables you have, I think the more you'll need to rely on tables to present that information. Be very clear about your assumption checking and your findings from that. You need to report your descriptive statistics to illustrate the core findings. It's just identifying a statistically significant F ratio won't help much. So you need to just be clear about the actual means of your groups and standard deviations and so on. And you should, as good practice, report measures of effect size and ideally confidence intervals. So that could be confidence intervals around the mean or confidence intervals around the mean difference, that sort of thing. And again, if you have a look at your guides, you'll get an idea of some of these things, but also look at published literature, for example, those articles in the PLOS One journal. You'll get a sense of they've all been published fairly recently. You'll get a sense of kind of reporting these things and what's useful. Strengths of ANOVA is that it's fairly robust to some of the violations, and actually if you've got a simple ANOVA you're doing, a fairly straightforward ANOVA, there are lots of ways of correcting for those violations too. You can look at main and interaction effects, which if you were trying to do this in regression would become quite hideously complicated. That it is doable, but it would be very difficult. So actually ANOVA can make this a lot more straightforward, even though technically you could potentially use either. ANOVA, if you've got categorical independent variables, will make exploring main and interaction effects just so much easier. And it's versatile, it's commonly used. People, in social sciences are quite used to interpreting findings from them, so it's a good tool to be able to use and to know when it's being used well. And as you've seen, it can help you to answer all sorts of different research questions. The limitations are, and the misuse are, that it can get very complicated very quickly. So if you can, you should keep your analysis simple. It would, the more independent variables you include, the more challenging it is, particularly to interpret really complicated interactions. There are a lot of misunderstandings if you read Bryce-Burt's paper about power and sample size issues, particularly around repeated measures ANOVA. Researchers consistently underpower their studies, and it's a prevalent issue. So actually, you may need more data to do your ANOVA, even if it's a straightforward one-way ANOVA, than you might think. So you should be aware of that. And there are very different opinions on how data should be checked, how the assumptions, what you need to do to check the assumptions have been satisfied, and actually when the assumptions have been satisfied, there are differences in opinion. So be clear about which approach you've taken, which guides you use to help with your decision making, and that should stave off critique or criticism. That was a whistle-stop tour of ANOVA, how it works and so on. Hopefully you've got an idea of when you would use it, what you can do with it, what you need to do if your data isn't behaving perfectly, as it often doesn't, and some of the strengths and limitations of ANOVA. In terms of suggested reading, I've put some links here to kind of blog posts that are useful, a link to guides for calculating sample size. I found a book that has been shared now by Tabachnik and Fiddle on experimental designs using ANOVA, so that's really useful. And if you want to look at how this is done by hand, then I'd recommend using Laughlin's YouTube channel. It's really good. It takes you through step by step, and I think that will illustrate some of the issues that we've been describing. Those are the references for this session. I hope you found it useful. We will be discussing this in block 2, so if you do have any questions, feel free to bring them then, but also post them to the discussion forum. Okay, thank you.